Hello everyone, welcome to the online lecture for ME 5030. This is lecture number 6, which will be seen on April 9th, Thursday at 11 a.m. I guess it should be called a.m. here, not p.m. Alright, so plan for today's lecture is I want to do two things. I want to first of all solve a problem on the Lagrange multipliers. This is still for a holonomic system. Next week I'll do a non-holonomic system, and then we will go on to look at a spinning top and so on. Okay. Then what I also want to do is I want to give a very brief recap of the different types of Lagrangian formulations that we have seen so far. Okay. So the aim for today's lecture is the following two things. So aim is to solve a problem using Lagrange multipliers for a holonomic system. Okay. And then the final aim of this lecture is to essentially give a brief review of the Lagrangian formulation for different types of cases. Okay, a brief review of the Lagrangian formulation for different cases. Okay. All right, so this is the situation that we are going to be looking at. The problem that we will be solving is a fairly straightforward problem. Once again, a 2D problem. Next week is when I will start doing 3D stuff. The next couple of weeks, which are our last weeks of online lectures, I'll do the 3D stuff where we'll do a rolling coin and then a spinning top. Okay. So for this problem, I'm just going to first of all draw the figure for the problem. Okay, so problem. So in this problem, this is a fairly standard problem as well, as you might recognize by looking at the figure. I have a wall which I'm going to draw as the xy plane. Okay, so here is the wall, and this is the x and the y direction. So this is y, and then this is x, and let's say that the unit vector along this direction is ey as usual. Okay, and then the unit vector along this direction is ex. Okay, and let me call this as point O. Okay, now on this wall I have a rod which I'm going to draw in the following manner. The rod itself is massless. Okay, so we're going to neglect the mass of the rod, but at the end of the rod I'm going to have two point masses. Okay, so I'm going to draw one of them here. Okay, and so which means that I have to take this rod and kind of set it out here, and then I'm going to take that and duplicate that, and I guess I'll make it a different color and bring it out right here. Okay, and let's move that a little up. Okay, and let me change the color filling of that. I guess the fill color is what I need to change. All right, so here is the situation. Let's call this end as the end A of the rod. Okay, this is end A, and then this is end B, and then this is of length L. Okay, now this is a massless rod. Okay, these are particles or point masses here. Okay, this is point mass. Let's say the mass of that is m suffix b, and then here is a point mass m suffix a. Okay, so here is the situation. For this particular problem, I'm going to ignore friction. It is not a big deal to add in friction. We just add it as a QNC, right, a non-conservative force. Okay, and then another problem that I'm going to solve next week, we will have some non-conservative forces on a non-holonomic system. So it's going to be a pretty messy problem, I can tell you right away. All right, so here is the situation. We're going to say, okay, this is the direction of gravity. Okay, and we're going to ignore friction. Okay, which means that this is going to be a conservative system. Okay, and what do we need to do in this particular problem? So in this problem we got to obtain the equation of motion for the system of the two masses connected by a rigid massless rod. Okay, so this is a massless rod and this is also a rigid rod. Okay, then that's the first thing that we need to do, and then we also need to obtain an expression for the constraint forces on the system using the concept of Lagrange multipliers. Okay, so that's a key thing here. So we need to obtain the equation of motion for the system. The other thing is we need to obtain an expression for the constraint forces, or the constraints, I would say constraints, acting on the system using the concept of the Lagrange multipliers. Okay, all right, and so this is the problem that we need to solve. So I'm going to take this problem, copy it down, and we will start off by looking at configuration coordinates, what are the constraints, and then we will look at the idea of how to use the Lagrange multipliers here. Okay, so let me take this system here, and I'm going to clean up some parts of this system, okay, as I copy it and paste it. So I'm going to copy that and bring it down here, I guess, paste it here. So let's set it up at this corner. Okay, I'm going to get rid of some of these things. We know what these things are. Okay, this is a point mass here, so I'm going to cut that out. I'm going to cut some of these things out as well, and cut that creature as well. I guess that is not a good thing. Okay, so I'm going to cut that out. Okay, all right, so first of all we need to set up the configuration coordinates. So what are the configuration coordinates? Configuration coordinates. So for particle A, and what I'm going to do is I'm going to implicitly assume a planar problem. Okay, so we're going to assume a planar problem. Okay, and for particle A, I'm going to say that the configuration coordinates are the positions xa and ya with respect to the point O, which is a stationary observer. Okay, this is position of mass ma as seen by a stationary observer at O. Okay, then for particle B, or the point mass B, I'm going to call them as xb and yb. This is the position of mass mb as seen by a stationary observer at O. Okay, so these are the two things. Now if okay, let me go to the non-planar case once we go past the constraints and so on. Okay, so the total number of configuration coordinates, which means that the total number of configuration coordinates is equal to 2 plus 2, which is equal to 4. Okay, this is the total number of configuration coordinates. Okay, then what are the constraints? Okay, constraints. There are a couple of constraints that I'm going to impose. I'm going to say that particles A and B do not lose contact with the wall. So this is something that I want to add on to the problem itself. So I'm going to go here and say we're going to assume that particles A and B. So I'm going to make a note here. Note. We're going to assume A and B do not lose contact with the wall. Okay, and of course this is the wall here. If you want to draw it as we typically draw a wall. Okay, and likewise the same situation here as well. So this is the wall that we are talking about. This same problem can be made into a much more formidable problem by saying that okay, the bar is no longer massless, it has a mass itself, which means that it has to be treated as a rigid body, so you're going to have rotational kinetic energy and so on. It is not a big deal, it just becomes a little messy. Okay, so here are the constraints. First thing is the particle A never loses contact with the vertical wall. Okay, the second constraint is particle B never loses contact with the horizontal wall. And quite obviously the third constraint is that the length L is a constant, or the distance from point A to point B is a constant. Okay, the length or distance from A to B is fixed length, and that's equal to L. Okay, so this is what we have so far. Now we want to cast these in the form of equations, but before that we see that okay, all the constraints are holonomic, because you see that particle A never losing contact to the vertical wall, that's a geometric constraint. It's physically restrained from losing contact because of the presence of the wall. Okay, particle B never loses contact to the horizontal wall is also a geometric constraint. And then lastly, the distance constraint is a geometric constraint as well. So all the constraints are geometric or holonomic, or geometric or holonomic, and this can also be proved using the test for integrability if you want. Okay, after writing the constraints in the Pfaffian form. And this is something that we will be doing as we go down into the problem. We will be writing all these constraints in a Pfaffian form. But the key statement here is all of these are geometric or holonomic constraints, which means that the system is a holonomic system. Is because all the constraints, all three constraints can be shown to be holonomic. Okay, so that's the key statement that I wanted to make here. Okay, so the system is holonomic, and once we have that, we can then say that, okay, the number of degrees of freedom, okay, the number of degrees of freedom is equal to the number of configuration coordinates minus the number of constraints. Okay, so which means that this is going to be equal to 4 minus 3, which is equal to 1. Okay, this means that the system has a single degree of freedom, and I will expand on this point later down the line in this lecture. Okay, all right, so that's great. We have a holonomic system, and the number of degrees of freedom is 1, and since the system is holonomic, I can come up with a generalized coordinate which is equal to the number of degrees of freedom by selecting some kind of a variable. So I just want to make a note here. Okay, so note that since system is holonomic, we can come up with a generalized coordinate, or we can come up with generalized coordinates. Let me erase that and write it here. We can come up with generalized coordinates to describe the equation of motion of the system. Okay, to describe the equation of motion of the system, and in this case the number of generalized coordinates is equal to the number of degrees of freedom. This is true for a holonomic system only. Okay, for a that is something to keep in mind all the time. All right, but I'm not going to be using that idea right now. I'm just going to be expanding on the configuration coordinate. So my first step is to write the constraint equations in the Pfaffian form, then start using the idea of Lagrange multipliers. Then I have to go back to Newtonian mechanics to see what exactly these multipliers mean, and then towards the end, we will summarize the Lagrangian formulation, and if we have time, I'll come back to the same problem and look at what the equation of motion is using a generalized coordinate. Okay, so here are the steps to be taken. So write the constraints equations in the Pfaffian form. Okay, then that's the first thing. Then use the multipliers. Plus the configuration coordinates. Okay. To get the constraint forces, this will involve may require use of Newtonian mechanics as well. Okay, that's something that is a drawback of the Lagrange multiplier method. It's not very elegant. It is just a mathematical technique. But sometimes you have to solve problems using the Lagrangian formulation. So this is the way to go forward. Okay, let us write the constraint equations in the Pfaffian form. Okay, so constraint equations. Okay. Now, one thing that we can do is we can write the configuration coordinates in the form of Q1, Q2, Q3, and Q4. I'm loath to do that because I want to show you what's actually going on. So one quick note that I want to make here. Okay. we can write configuration coordinates as the following. Okay, xa is equal to q1, ya is equal to q2, xp is equal to q3, yb is equal to q4, and then write the Pfaffian form of the constraints and then solve the problem. Okay, this is something that you can do, but I'm going to avoid doing that just for the sake of simplicity. I will avoid doing so. That is, I will avoid using these Q1s, Q2s and Q3s. Okay, I will avoid doing so. That is, I will avoid using the Q1, Q2, Q3, etc. and directly use XA, XB, etc. to solve the problem. Okay. Of course, this is quite anathema to an actual dynamicist, but I just want to make sure that we understand what we are doing here. Those Q1, Q2, Q3s, and Q4s are going to be immensely confusing if you start looking at them without any context, and so I don't want to do that, and I don't want to lose the crowd. All right, so I'm going to write the constraint equations. Okay, so constraint equations are the following. Okay, so J is equal to 1, the first constraint equation. This constraint says that what is the constraint? The constraint, if I move back and show you, this is that particle A never loses contact with the vertical wall, which means that for particle A, if you look at it, the location XA is always going to be equal to 0. So maybe I should take this figure here and then bring it back down below, because I'm just going to copy that and bring that here. Okay. So I'm going to bring that figure here and maybe reduce it in size. So the first constraint equation is that XA is equal to 0. Okay. All right. That is, the particle never loses contact, and the travel of the particle A is only in the y direction. Okay. And so if I start doing the differentiations and so on, then I can see that, okay, dxa by dt is equal to 0, which means that dxa is equal to 0. So if I write it in the Pfaffian form, I'm going to have 1 times dxa, then I'm going to have 0 times dya, 0 times dxb, 0 times dyb is equal to 0. Okay, this is the Pfaffian form of the first constraint. All right, then the j is equal to 2 constraint will just refer to the figure above. Okay, so the second constraint equation. This is also fairly straightforward. If you look at the motion of particle B, this is just going to start traveling along the x direction. So the coordinate yb is going to be equal to 0, which means that dyb by dt is equal to 0. So dyb is equal to 0, which means that if I write it in the Pfaffian form, I'm going to have 0 times dxa, 0 times dya, 0 times dxb, 1 times dyb is equal to 0. Okay, this is the Pfaffian form for the j is equal to 2 constraint. I'm just going to copy this and then bring that down here. Okay, and this is the Pfaffian form for the j is equal to 2 constraint. All right, then we go to the third constraint, okay, which is j is equal to 3, the distance between A and B is fixed and it's equal to length L. And so if I look at the distance, the coordinates of A are XA and YA, so this is going to be XA, YA. The coordinates of B are XB, YB, which means that the following should be the statement. Okay, this says that XA minus XB square, YA minus YB square is equal to L square. Right, this makes sense. This is the formula for distance square. Okay, I'm going to start differentiating on all sides with respect to time t. So this tells me the following. Okay, this is going to be and I'm going to use the chain rule for each of these. So this is going to be 2 times XA minus XB dxa by dt, then 2 times XB minus XA. I can shift the way it is written here. Okay, 2 times XB minus XA, then this is going to be dxB by dt, and then I'm going to have 2 times YA minus YB dya by dt plus 2 times YB minus YA dyb by dt is equal to d by dt of L square, which is equal to 0 because the length is fixed. I'm going to get rid of the factor of 2 everywhere. Okay, so that's gone, that's gone, that's also gone, that's also gone, and then I'm going to cross multiply by the term dt and rearrange this in the form that we've written the other constraints. So this is what I'm going to be having, which means that XA minus XB dxa. Okay, then I have YA minus YB dya, and then I'm going to have XB minus XA dxB, YB minus YA dyb is equal to 0. This is the Pfaffian form for the third constraint. I'm just going to bring that down here, okay, and paste it. This is the Pfaffian form for the third constraint. Let me get rid of some of these things here. Okay, and this is for the j is equal to 3 constraint. All right, so we have everything done here. Then what I'm going to do is I'm also going to write the potential energy, the kinetic energy. Because I'm using Lagrange multipliers to look at the constraint forces, I'm going to use the configuration coordinates. That's an important point to make. Okay, so note again. Okay, because we are interested in the constraint forces. We use the Lagrange multipliers. Which implies that we have to write the Lagrangian formulation using configuration coordinates. That is very, very important. Okay. All right, and so that's the key step here. If I'm using Lagrange multipliers, I'm interested in the constraint forces, so I have to use the configuration coordinate. So this is the general form. Okay, so general form for the ith configuration coordinate. We have the general form as d by dt of dl by dqi dot is equal to dl by dqi qi non-conservative, which is the non-conservative forces and torques that might be acting on this body, which we don't have any here, and then summation from J is equal to 1 to M lambda J AJI. Okay, and another note is that we're going to have as many multipliers as the number of constraint equations that we are utilizing. Okay, we will have as many multipliers as the number of constraint equations we are employing in the problem. Which means that for us, our problem, we will have 3 multipliers. Okay, that's something to keep a note of. All right, and so we are now ready to write the kinetic and the potential energies, and then go forward with the rest of the problem. Okay, kinetic and potential energies are fairly straightforward. Let me do that very quickly. So we got to write kinetic and potential energies. Write kinetic and potential energy of the system in terms of configuration coordinates. Reason being, we are using Lagrange multipliers. If you use Lagrange multipliers, you got to use configuration coordinates. If you don't use Lagrange multipliers, you use the generalized coordinate. This is a very, very key statement, and I'm going to summarize this again when we write a brief review of the Lagrangian formulation towards the end of this lecture. Okay, so for me, if I go back and bring the figure that I had in the past, okay, so if I bring this figure here, okay, copy that and bring that here, it's fairly easy to see the following. Okay, velocity of particle A is going to be xa dot in the ex and ya dot in the ey. Resist the temptation to apply the constraint equations right away. Okay, velocity of B is x dot ex for the particle B, y dot b ey. Okay, resist the urge, note resist the temptation to use the constraint equations. Okay, right away. That is because you know the fact that xa is 0, do not xa is a constant, do not cancel off xa dot right away. Please hang on to it, and then we will do the cancellations later on. Okay, all right, and then we will also say the following. Okay, the height for the particle A from a datum, so I'm going to call this as the datum. Okay, this horizontal line here is my datum. Okay, the height of particle A is going to be ya. Okay, so I'm going to call that as ha, and I'm going to call this little height here, which is going to be hb. Okay, and so for me, ha is a positive height, it's plus ya, hb is plus yb, positive height, because above the datum. Okay, that is an important point. Alright, so we are now ready to write the velocity of particle A, velocity of particle B, and then the kinetic and the potential energies, which means that velocity square of particle A is the following. Is xa dot square and then ya dot square. Velocity of particle B square is xb dot square yb dot square. Okay, and then the kinetic energy T is the total kinetic energy and this is going to be the net sum of the kinetic energies of particles A and B. So this is going to be TA plus TB, which means that T is this is the kinetic energy of the system. Okay, this is going to be half MA VA square and then half MB VB square. Okay, which means that kinetic energy T is going to be half MA XA dot square half MA YA dot square half MB XB dot square half MB YB dot square. Okay, these are the kinetic energies, and then if I write the potential energy, V is going to be the total potential energy, and this is going to be VA plus VB. Once again, I want to say, resist the temptation to use the constraints directly. Okay, that holds true for each of these. Okay, I'm sorry, that holds true for all of these. Okay, so from now I can say that V is MGHA MAGHA, I'm sorry, and this is MB GHB. HA and HB are positive heights, which means that V is going to be MAGYA and MBGYB. All right, and so for me the Lagrangian is going to be the following. L is T minus V is the Lagrangian of the system. Okay, and so I have the following. L is half MA XA dot square half MB XB dot square half MA YA dot square half MB YB dot square minus MA GYA minus MB GYB. Okay, this is the Lagrangian. Then I want to write the constraint equations as well. Okay, constraint equations are the following. J is equal to 1 equation. I have 1 times dxa and then 0 times I had it written in a particular order, so I want to continue that order, so I just want to go back, and so dya came next. Okay, so 0 times dya, then 0 times dxb, 0 times dyb is equal to 0. Okay, and if I write this in the Pfaffian form, if I compare it, this is going to be a11 dq1, a12 dq2, a13 dq3, a14 dq4 is equal to 0, or I can write this as a1 xa and a1 ya, a1 xb, a1 yb, and so on. It's not necessary, so but if I just do the comparison of the coefficients, I get the following. Okay, those are the coefficients here, so which tells me that a11 is 0, a12, I'm sorry, a11 is 1, apologies, a12 is 0, a13 is 0, a14 is 0. Okay, this is the first set of the Pfaffian coefficients. Okay, these you can call them as the Pfaffian coefficients. For the j is equal to 1 constraint. Okay, for the first constraint, and likewise I can do the same thing for the second constraint. So j is equal to 0 times dxa, 0 times dya, 0 times dxb, 0 times dyb is equal to 0. Compare this with the Pfaffian form: a21 dq1, a22 dq2, a23 dq3, a24 dq4 is equal to 0. These are all holonomic scleronomic constraints. Okay, so there is no time component involved here. If I do the comparison, then I get the following. Okay, so I get a21 is equal to 0, a22 is equal to 0, a23 is equal to 0, a24 is equal to 1. I missed out on a 1 here. My apologies for that. Okay, we know the dyb is the one that has the 1 term here. Okay, so that's the Pfaffian coefficient for the j is equal to 2 constraint. Okay, so this is the same as the above. I'm just going to copy that and bring that down here. And this is for j is equal to 2, the second constraint. We are almost on our way, you know. And the j is equal to 3. Here is the form of the constraints. Okay, this is j is equal to 2, this is j is equal to 1. The third constraint equation, I have xa minus xb dxa plus ya minus yb dya, xb minus xa dxb, yb minus ya dyb is equal to 0. Or compare this with a31 dq1, a32 dq2, a33 dq3, a34 dq4 is equal to 0, which tells me that a31, let me write the 3 properly, so a31 is xa minus xb, a32 is ya minus yb, a33 is xb minus xa, and a34 is yb minus ya. Okay, and these are the Pfaffian coefficients for the j is equal to 3 constraint equation, the third constraint equation. I'm just going to copy and paste that here. Okay, so this is for j is equal to 3 constraint. Okay, so we are almost on our way, and here is what I want to do. I want to write down the Lagrange formulation for each of these and then knock off some of the terms, and then we will be on our merry way. Okay, all right. So let's start off with the first one. Okay, so the Lagrange formulation using the multipliers. For I is equal to 1, so the Lagrange formulation with multipliers. Okay, so we say that here I is equal to 1 means that xa is the same as q1. Okay, and if that is the case, I have d by dt of dl by dxa dot. This is equal to dl by dxa, and then qxa non-conservative, and then summation j is equal to 1 to 3 lambda j aj1. Then I is equal to 2 implies this is for y a, which I call as q2. Okay, it doesn't matter what you call as q1, q2, and q3 and q4. It makes no difference. I'm just using ya here because I used the same form to write the Pfaffian equations. I have xa, ya, xb, and yb. Okay, it's all the same thing. This is going to be d by dt of dl by dya dot. This is equal to dl by dya plus q ya nc, and summation j is equal to 1 to 3 lambda j aj2. Then I is equal to 3 is xb, which is playing the role of q3, and so the equation becomes d by dt of dl by dxb dot is equal to dl by dxb qxb nc, j is equal to 1 to 3 lambda j aj3, and lastly I is equal to 4 is yb, which is equal to q4. This is d by dt of dl by dyb dot is equal to dl by dyb qyb non-conservative, and then summation j is equal to 1 to 3 lambda j aj4. Lots of things are going to get cancelled off. I don't have any non-conservative forces, so I'm going to knock off all of these terms right there. Okay, and then I'm going to start expanding them out, which tells me that here I have the following. So let me start off with the first one. Okay, so let us get into the root of the problem. Okay, get into the problem. So the Lagrangian, if I want to bring it down here, here is a Lagrangian. Okay, I'm going to copy that and then bring that down here. So this is what we had from before. Just want to make a quick note of this. This is what we had from before. Then we also had all these coefficients a11, 12, 13, 14, and so on. So I'm going to bring them all as well. Okay, so all of these, copy them and then bring them here. Okay, get rid of some of these terms. This is the second thing that I'm bringing down. Then the third thing I'm going to be bringing down is coefficients for the second constraint equation. So that's this creature right here. Okay, copy that, then bring that here. And the last thing is the coefficients for the last equation. Okay, which is this guy right down here. Okay, so bring this creature, copy that, and then I'm going to bring that here. Okay, so this is the last one that I have, and I think this is a good place to start filling up the gaps for us. So I'm going to look at the first equation. Okay, so the I is equal to 1 equation. I'm going to have d by dt of dl by dxa dot. There is only one term containing xa dot in the Lagrangian, so that's going to be ma differentiation of xa dot square. Half term goes off. This is going to be dl by dxa, so that's going to be a term which is 0, right? The Lagrangian does not contain any terms containing xa. Then I'm just going to expand this as lambda 1 a11, lambda 2 a12, lambda 3 a13. Okay, and this is the term which says dl by dxa is equal to 0. Okay, then I do the same thing for I is equal to 2. I'm going to have d by dt of m, in this case this is going to be, when we did I is equal to 2, this was ya, right? So this is going to be ma ya dot. Are there any terms containing ya in the Lagrangian? There are a couple of, there's one term there, so that's going to be minus ma times g, right? Differentiation of ya with respect to dya. Okay, the Lagrangian with respect to dya. Then I'm going to have plus lambda 1 a 1 2, lambda 2 a 2 2, lambda 3 a 3 2. And I made a mistake here, so this is a 1 1, this is going to be a 2 1 and a 3 1. I apologize for that. I'm just sometimes, so this is a 1 1, this is a 2 1, this is a 3 1. Okay, and then I have two other things that I'm going to write down. I is equal to 3, where we have d by dt of mb xb dot, which is equal to 0, and then lambda 1 a, this is I is equal to 3, so this is 1 3, lambda 2 a 2 3, and then lambda 3 a 3 3, and then the last one I is equal to 4, where we have d by dt of mb yb dot, which is equal to minus mbg. Notice that the Lagrangian contains the term yb. So, and I'll recap all of these again as we look down. So lambda 1 a 1 4, lambda 2 a 2 4, lambda 3 a 3 4. Okay, and we have used the above in this. I'm just going to write that in blue. Okay, so dl by dxa dot is ma xa dot dl by dxa is equal to 0. Okay, we use that here, and then where we used dl by dya dot is, if I do the partial derivative, that's going to be maya dot dl by dya. Be careful, that is the force of gravity. And then we have dl by dxb dot, which is mb xb dot, dl by dxb was 0, and then lastly dl by dyb dot was mb yb dot dl by dyb. Look at the Lagrangian, you're doing partial derivatives, keep that in mind. Okay, this is a partial derivative term here. Okay, so this is dyb, and this is going to be minus mb times g. Okay, so these are all the things that we had used above. Okay, and then I'm sorry, there are a couple of things that I can also cancel off. Okay, if I take a look at a 1 2 a2 1 and a3 1, you look at a2 1 at 0, a3 1 is non-zero, so I can just get rid of this particular term here. Then I see that a1 2 is 0. Okay, then a2 2 I also see is 0 in the second equation. The third equation I see that a2 3 is equal to 0. Do I have an a1 3? I don't have an a1 3 right there, so that's also gone. Then I have an a1 4, which is equal to 0, but a2 4 is not 0, that's equal to 1. a3 4 is not 0. Okay, so we have done a couple of these simplifications, so I'm just going to rewrite some of these terms once again. Okay, so get back to solving the problem. So for I is equal to 1, we have d by dt of maxa dot is going to be maxa double dot. Okay, so this is going to be maxa double dot. This is going to be, and if I go back to the equation, it's lambda 1 a1 1. Okay, so that's going to be lambda 1 times 1, and then lambda 3 times xa minus xb, where we have used a1 1 is equal to 1, and then a1 3, I'm sorry, a3 1 is xa minus xb. Okay, that's something that we have used. Then I go to the next equation. I is equal to equation mb xb ya double dot, I'm sorry, ma ya double dot. This is going to be, if I go back, I see that there is minus mag, that term is there. Then I don't have lambda 1 lambda 2, but I have a lambda 3 a3 2, so this is going to be plus lambda 3 times ya minus yb, where we have used A32 to be ya minus yb. And likewise, I keep going. I is equal to 3. I have mb xb double dot, and this is, if I go back to the I is equal to 3 equation, I have lambda 3 a33, so this is going to be lambda 3 times xb minus xa, and we have made use of the fact this is going to be a33 is xb minus xa. Okay, and lastly, I is equal to 4, I'm going to have mb yb double dot is equal to, look at the I is equal to 4 equation, minus mbg, do not forget that. Okay, minus mb times g minus mb times g. Then I have a couple more things going on. I have lambda 2 times a24, which is equal to 1, as you can see, and then a34, which is yb minus ya. So this is going to be plus lambda 2 times 1 plus lambda 3 times yb minus ya. And here we have used a24 is equal to 1 and a34 is yb minus ya. Okay, now I'm going to start using the constraints. Okay, now start using the constraint equations to simplify more. And what are the constraint equations? I have xa is equal to 0, which means that xa double dot is equal to 0. I have yb is equal to 0, which means that yb double dot is equal to 0. So wherever I see these kinds of terms, I immediately see that xa is right there. So I'm just going to strike off some of these things. So that term is going to be gone. Wherever I have an xa, that term is also going to be gone. Then wherever I have a yb, that term is going to be gone. And you see that if I have an xa, that term is also going to be gone. If I have a yb double dot or a yb, that term is going to be gone, and that term is also going to be gone. Okay, this is by making use of the constraints equations. Okay, so we are making use of these in the above. And so now I have a much more simpler situation. Okay, if I start looking at after the simplification, I have the following. For I is equal to 1, it's fairly simple. Lambda 1 plus lambda 3 times minus xb is equal to 0. So 0 is lambda 1 plus lambda 3 times minus xb, which means that lambda 1 is xb times lambda 3. So that is one thing that I have. I'm going to call that as a. Then I is equal to 2 tells me the following. Okay, ya double dot is not 0, so I'm going to have ma ya double dot is equal to minus ma times g plus lambda 3 times ya. Nothing going on here. Okay, then I is equal to 3. I have 0 is equal to minus well, I don't have 0 for that, I'm sorry. I have mb xb double dot is equal to lambda 3 times, if I look at that, that's going to be xb, which is quite obvious. And then I have I is equal to 4, which is 0 because yb double dot is 0, minus mbg plus lambda 2 plus lambda 3 times minus This is going to be YA. I just want to make sure. Okay, that's yeah, minus YA. Okay, which tells me that lambda 2 is MBG plus YA times lambda 3, and I'm going to call that as equation D. This is equation B, and this is equation C. All right, now here is what I'm going to be doing. I'm going to be taking equations B and C, okay, and rewrite them. Okay, so if I just isolate the lambda 3 terms, I'm going to have lambda 3 times YA is equal to MA YA double dot plus MA times G, and then I have lambda 3 times XB. This is equal to MB XB double dot, right? This is from equation B. This is from equation C. And what I'm going to do is I'm going to take this entire equation and I'm going to simplify this by getting rid of lambda 3. So I'm going to multiply this by XB. Okay, multiply by XB. Likewise, multiply YA. Okay, and then subtract. Okay, which means that I'm going to get the following now. I have lambda 3 YA XB is equal to MA XB YA double dot MA XB times G. Lambda 3 times XB times YA, same thing, is MB XB double dot times YA. Okay, and then if I subtract the two equations, here is what I end up getting. MA XB YA double dot plus MA XBG is equal to MB YA XB double dot. I'm going to call this as equation E. Okay, this is a crucial equation. So I have equations A, B, C, D, and E. Okay, I'm going to take it a step further. I'm going to bring in my next constraint equation. Okay, bring in the last constraint equation. And what is the reason for that? The reason for that is, you see, if I bring in the last constraint equation, I have a relationship between XB and YA, which means that I can get rid of either XB or YA from equation E and obtain the equation of motion for this body. It's actually a single degree of freedom system, so my equation is going to be either in terms of XB or YA. Okay, the reason for that is the following. Okay, okay, look at equation E. By using the last constraint equation, the J is equal to 3 equation, we can replace XB with YA in order to get the equation of motion of the system. Right, because it's a differential equation. The equation E is a differential equation, and once I have the equation of motion, then it's not a big deal. I can make use of that to find lambda 3. Once I find lambda 3, I can find lambda 1 and lambda 2, and we will talk about that in a minute. Okay, so here is what I'm going to be doing. So the J is equal to 3 constraint equation is the following. Okay, it is xa minus xb square ya minus yb square is equal to L square, but then I already have a constraint saying that xa is 0 and yb is 0, so I have the following, which means that xb square plus ya square is equal to L square, which tells me first of all that xb square is equal to L square minus ya square. Okay, then differentiate the above once with respect to time. Use the chain rule. Okay, I'm going to be getting 2xb dot is equal to 0 minus 2 ya dot, and obviously the factor of 2 will be cancelled. Okay, which tells me that xb dot is equal to minus ya dot divided by xb. Okay, so I have some nice things going on here. I'm going to call this as 1. Okay, I'm going to call this as 2, and then I'm going to differentiate this one more time, okay, to get the acceleration. Differentiate once more with respect to time, and I'm going to skip some steps here in terms of the differentiation. So here is what I'm going to end up getting. Okay, I'm going to have xb double dot is equal to minus ya dot square minus xb dot square minus ya double dot, and I'm sorry, this has to be gotten rid of. That's not what I wanted. Okay, ya double dot here, all of this divided by xb. Okay, and this I'm going to be calling as 3. Okay, and I kind of took some liberties here in terms of the differentiations and all that I have done. Okay, all right. I guess we shall proceed with the rest of the problem now. So here is what I'm going to be doing. I'm going to use equations 1, 2, and 3 and substitute that into equation E. Okay, here is equation E. Okay, then the next step, take 1, 2, and 3 and substitute equation E. And what is equation E? Is the following, right? I had if I bring that creature down here, okay, copy that and I bring it here. Okay, I bring that here. So I'm going to substitute for the following term. So I'm going to substitute for xb. I'm just going to darken it in blue color. Substitute here and then substitute for xb double dot. So I'm going to do the substitution for xb double dot first. Okay, watch this. Okay, so substitute for xb double dot first. Okay, I get ma xb ya double dot plus ma xbg. This is equal to mb ya. Xb double dot was the following. You will have that as minus ya dot square xb dot square minus ya double dot, all of that divided by xb. Okay, that's what I had. And if I point this out, so all I did was take that term there and then substitute in there. Okay, that's what I did. And once I do that, then I also start simplifying. I cross multiply by xb on both sides, okay, so that I have ma xb square ya double dot ma xb square g is the following: minus mb ya dot square minus mb ya xb dot square minus mb ya square ya double dot, right, as you can see. Okay, which means if I bring everything onto the left hand side, I get the following. So this is going to be ma xb square plus mb ya square ya double dot. Then I'm going to have two more terms. Okay, it's a ya dot square, that's going to be mb ya dot square. Then I'm going to have mb ya xb dot square plus ma xb square g is equal to 0. Now substitute xb square is equal to L square minus ya square into above equation, and also substitute xb dot is minus ya dot by xb, which means xb dot square, I'm just squaring on all sides, ya square ya dot square by xb square, which is ya square ya dot square divided by L square minus ya square. You see how painful this problem is. Okay, here is what I did. I took these and I substituted there. Okay, I just want to draw it out a little better. I'm going to take that and substitute that in there. I'm going to take that and substitute it into this above equations as well. Okay, wherever I see an xb square, and then I'm going to take this x dot b square and substitute that into this term here. So I'm going to take that and substitute that here. Okay, so I'm going to do these substitutions, and here is what I end up getting. Okay, so substitute for xb square and xb dot square into the differential equation. For ya, and you can obviously do the opposite as well. I can write everything in terms of xb instead of writing everything in terms of ya. That is also completely fine. Okay, note quickly, can also write equation of motion in terms of xb rather than ya. Okay, this is completely fair. There is nothing wrong with that. Okay, if I do the substitutions, then here is what I end up getting. Okay, so I have after the substitutions mb ya square, and then ma xb square is L square minus ya square ya double dot. That's one thing. Then I'm going to be having plus mb ya dot square. Then I'm going to be having ma times L square minus ya square times g plus mb ya times ya square ya dot square by L square minus YA square. This is equal to 0. Or finally, equation of motion in terms of YA is the following. Okay, it's going to be MB YA square MA times L square YA square YA double dot plus the equation of motion above in the box. and here is what I'm going to be doing. And here is our figure from some time back. Okay, I'm just going to scoot up and then bring that fellow down here. Okay, all right, here is that guy. and then that. Okay, so these are the free body diagrams, kinetic diagrams, free body diagram of B, kinetic diagram of B. All I have to do is for each particle, if I sum forces in the x and the y directions, okay, so for each particle,
You're the best in the world.
to equation C. It's a fairly straightforward comparison. Okay. and here is equation 3. Just bring this creature down. Okay, copy that and bring that here, and I'm just going to rewrite equation C. Okay, equation C is going to be the following: xb, let me write it in black color, xb times lambda 3 is equal to mb xb double dot. This is equation C, and if I do the comparison, this tells me that lambda 3 is T by L, right? And so we see that the constraint forces can be obtained by the Lagrange multipliers. Okay, so once we solve for lambda 1, lambda 2, lambda 3 as described earlier, we can obtain lambda 1 is equal to NA, lambda 2 is equal to NB, and lambda 3 is equal to T by L, or T is equal to lambda 3 times L. Alright, so this problem was solved using the idea of Lagrange multipliers, and a pretty laborious process. Of course, we had to make use of all the equations that we had at our disposal. The last few steps are the most important steps. We solve the equation of motion. This is the equation of motion. Once we do that, then we find out lambda 3. Then once we find lambda 3, we find lambda 1 and lambda 2. Okay, so if you want to write like a route map, once you solve for this, you find that. Okay, that's the first step. Then once you find lambda 3, then you can go back and find that, and then you can also use that to find that. Okay, once you find lambda 3, then you can eventually say that okay, the tension T is L times lambda 3, and then the normal force is lambda 1 and lambda 2, NA and NB. All right, so this is the end of this particular problem. Okay, all right, so this is the end of this problem. And very quickly, I just want to rewrite the Lagrangian formulation for some of these instances that we have seen. So two key notes that I want to make. Okay, note. Okay, in the first note, if system is holonomic and we are not interested in constraint forces, then we use the generalized coordinates and write the Lagrangian formulation in terms of generalized coordinates. Okay, this is important. So in this case, I have Qj is the jth generalized coordinate. Okay, and so if the system is holonomic and we are not interested in the constraint forces, then we use the generalized coordinates. Okay, and then in this case the Lagrangian formulation itself becomes the following. I'm going to have d by dt of dl by dqj dot is equal to dl by dqj plus qj nc. Okay, and typically qj nc can be broken into qj nc for forces that are velocity dependent. Then you might have forces that are velocity independent, and you might also have torques, right? This is velocity dependent, this is velocity independent, okay, and this is for torques, okay. For any applied torque. And we have seen how these forces have been handled earlier, okay, and I don't want to dwell too much on this, but typically if you have QJ, NC, velocity dependent, let me just take this particular creature, and then if I copy that and I paste it here, so this is typically written in the following fashion, okay. This is going to be summation, let's say I is equal to 1 to something. This is going to be Fi velocity dependent dot product with dri dot by dqj dot, okay. Then I'm going to have the velocity independent forces. In this case I'm going to copy that and bring that here, okay. Velocity independent forces, they can be written as some index, I, j, k, you can call it as k is equal to 1 to something, I don't know, whatever number, f k velocity independent dotted with, this is a dot product, drk by dqj, okay. Some index I, in this case I is the index for the velocity dependent forces, and in this case k is the index for the velocity independent forces, okay. And then lastly this torque term here, qj for the torque. Let me copy that and bring that creature here, okay. This is fairly straightforward as well. This is let's say summation some n is equal to 1 to something. This is going to be m n dotted with d omega n by dqj dot, okay, where n is the index for the applied torque, okay. All right, and this is for a holonomic situation, but if your situation is non-holonomic, or if you're interested in constraint forces, then here is what we got to do, okay. Second situation, this is my last point, apologies for going above board, okay. If system is non-holonomic, or if system is holonomic and we are interested in the constraint forces, then write the Lagrangian in terms of the configuration coordinates. That is an important term here, okay. So I just want to underline that. So if the system is non-holonomic, or if the system is holonomic and we are interested in the constraint forces, then you write the Lagrangian in terms of the configuration coordinates. As an addendum, you can say that if I say step 3, let me write that here, steps 3 for non-holonomic systems, we have to write Lagrangian in terms of the configuration coordinates. Okay, this is a must. We don't have a choice. We have to write the Lagrangian in terms of the configuration coordinates. Cannot come up with generalized coordinates. So for cases 2 and 3, okay, so for cases, I'm sorry, this is not the color I wanted. For cases 2 and 3, here is the Lagrangian formulation. Uses configuration coordinates and multipliers. Okay, and let's say that Qi is the ith configuration coordinate. Then for cases 2 and 3, we have d by dt dl by dqi dot is equal dl by dqi qi nc plus summation j is equal to 1 to m lambda j aji. Important point, this is a configuration coordinate or from the configuration coordinates. This is the multiplier term. This guy aji is from the Pfaffian form of the constraint. Equation, and QNC calculated as previously specified. Okay, this is calculated as before. All right, and one more point here, this qj here, these are all the generalized coordinate for the sake of a holonomic system, so I just want to point that out here. Okay, so maybe make a note of that. Okay, make a note of that. These are all generalized coordinates here. All right, so that's the end of this particular lecture. Sorry that I went a little beyond the usual lecture time, but I wanted to summarize all these different cases so that it is useful to us, and we will then be in a position to solve problems for non-holonomic systems as well. Okay, all right, thank you very much, and I hope all of you are staying safe and being healthy. Take care of yourselves. Bye bye.